All right, welcome back everyone. Today we're going to be talking about phase transformations of mixtures. And so as a first step, let's go back to thinking about our discussion of mixtures. We did a little bit of that in Chapter 2 when we talked about taking two equal volumes of ideal gases and mixing them together and calculating how much that mixing process changed the entropy of the system. We're going to revisit this idea, but in a little bit more of a generic way, not just ideal gases, but we're going to consider a mixture of two kinds of molecules, molecules A and B. And to begin with, we're going to assume that the molecules are the same size and interact with each other in the same way. In other words, that they have the same forces between molecules A and B as molecules A and molecules B and B. So that if we have a sort of a van der Waals interaction going on, for instance, that the interaction won't particularly care whether it's molecules of A and A interacting together, or whether it's molecules of B and B interacting together, or whether they are the same, or whether it's A and B interacting, and so on. This approximation is what we call an ideal mixture. And in an ideal mixture, the effect of mixing is just that we are taking we're taking the unmixed A and B, the pure unmixed A and the pure unmixed B, and we're allowing basically for swaps randomly between any two particles such that we end up with a mixed state of some sort afterwards. So that, in other words, the entropy then of mixing is just going to be the entropy of taking, if there are Na molecules of the A type, then it's a matter of taking so if there are Na molecules of type A and Nb molecules of type B, so that Na plus Nb is equal to the total number of molecules, then the entropy of going from the unmixed state to the mixed state, that change in entropy is just the entropy, or well, we could calculate the multiplicity of mixing is just the multiplicity of taking these Na molecules and arranging them in N sites, right? So that we're not changing anything about the configuration of our material, we're just swapping the different kinds of particles around. So in other words, this is Na, or N, choose Na. So that then the entropy of mixing, or the change in entropy of mixing, is just K times the logarithm of our multiplicity of mixing. So the K times the logarithm of N choose Na, or K times the logarithm of N factorial over Na factorial, and then the 1 minus Na is going to be the Nb factorial term. The N minus Na factorial term turns into the Nb factorial term. All right. Next step is we assume that that we have large numbers of each particle. In other words, that we're in a statistical limit where thermodynamics is going to be applicable anyway. So if we have Na and Nb are large, then we can apply the Stirling approximation. And so we replace each of these n factorials with an n log n minus n. So this is K times the logarithm of n log n minus n for the top n factorial minus, we're going to have an NA log NA, and now plus an NA term. And then also minus an NB log NB plus NB term. So we have a Stirling approximation expansion for n factorial, NA factorial, and NB factorial. Notice that this gives us a minus n in the front, but then a plus NA and a plus NB. And since the sum of NA and NB is at n, then we can cancel out all those single terms, and the entropy of mixing just becomes K times the logarithm of n log n minus NA log NA minus NB log NB. And if we want to rewrite this not in terms of NA and NB, but rather in terms of a fraction of the material is in one form and 1 minus that fraction of the material is in the other form, then we might say, for instance, we're going to let NA be 1 minus x times n, and NB we can let be x times n, so that x is the fraction of the material which is of type B, and 1 minus x is the fraction of the material which is type A. And if we then plug that into our entropy of mixing term, we can pull out, or we can rewrite that as, again, K times the logarithm of n log n minus 1 minus x, n log of 1 minus x times n, minus xn log of xn. Now each of these terms has an n sitting out in front, and so we can pull the n out front. We have nk times the logarithm of log n, and log n minus 1 minus x log of 1 minus x, and minus 1 minus x log of n minus x log x minus x log n. So we've expanded out both of these logarithms. We extracted the leading n on the front. Now if we collect the log n terms, nk log, there's this log n term in the front, so 1, and then there's a log n term here with a minus 1 minus x in front of it, and then there's this log n term back here, minus x. All of that is just going to sum to 0, so then 1 minus x log of 1 minus x and minus x log x. So that whole term goes away, and we're just left with the entropy of mixing here. Can be then written down as minus nk times x log x plus 1 minus x log of 1 minus x. Pleasingly, that's nice and symmetric with the two fractions. In other words, each fraction interacts or adds to the entropy of mixing in the same way, which is reassuring, because there's an arbitrary choice here that A and B, or how we label them. All right, so having established what mixing does to the entropy, we can now then look at how that's going to affect, or how that's going to play out in a system, in a thermal system, when that system is undergoing various thermal changes. And in particular, if the Gibbs free energy is driving our system, if the system wants to minimize the Gibbs free energy, then if we understand how the Gibbs free energy behaves in a mixture, then we can make some predictions for the thermodynamic behavior of mixtures under various conditions. So again, the Gibbs free energy, which I'm just going to start using GFE as a shorthand for that. The Gibbs free energy, again, has this form: G equals thermal energy plus PV minus TS. This is for a pure system. And if we label the Gibbs free energy of a pure amount of type A, and the Gibbs free energy of a pure amount of type B as these GA and GB super zero terms. These are the pure terms. Then we can label the Gibbs free energy of unmixed amount of A and B, right? So if there is an amount of 1 minus X of our substance is in the form of pure A, and X amount of our substance is in the form pure B, then the unmixed Gibbs free energy is just the sum of those two terms. A partial fraction of the amount of stuff is in A, and another partial fraction of the amount of stuff is in B. And for instance, then if we write down the total Gibbs free energy as a function of our fraction, so from 0 to 1, where this is pure A on the left and pure B on the right, and this is GA naught over here, and we'll say this is GB naught over there. Then if you have an unmixed admixture of GA and GB, or of A and B, then whatever your fraction is, the Gibbs free energy total of the unmixed will be this linear interpolation between the Gibbs free energy of pure A and the Gibbs free energy of pure B. All right, so if you have just chunks of A and B sitting around without mixing them, then the total entropy, the total Gibbs free energy will be on this straight line at whatever the fraction of A and B are. The closer you get to pure B, obviously, the closer the Gibbs free energy is to pure B. The closer you get to pure A, the closer the free energy is to pure A. But for a fixed fraction of A and B, you will have a Gibbs free energy somewhere on this line. Now, if we add into this equation, if we add into it the effect of changing the entropy of our system due to mixing, we can see that the effect of mixing then, if the change in entropy is increasing, would be to decrease the Gibbs free energy. So the change in entropy mixing is, again, minus nk times x log of x plus 1 minus x log of 1 minus x. And if we have, say, 1 mole of total substance here, so we're going to have a mole total of A plus B, then the total number n will be for 1 mole, and so we can replace nk here with the gas constant R for 1 mole. And then rewrite our Gibbs free energy as 1 minus x Gibbs free energy of pure A plus x amount of the Gibbs free energy of pure B, where now these are the Gibbs free energies of 1 mole each of A and B, minus this term for the entropy, R times x log x plus 1 minus x log 1 minus x. Let's think a little bit about what that's going to look like. So if we plot our entropy, our change in the entropy, on this plot going from pure A to pure B, it's going to have a concave down look to it. At pure A, it's over here. At pure B, it's over there. And if there is some amount of mixture between A and B, then there's going to be a concave up shape for the change in the mixing. The closer you get to a 50-50 mix of A and B, the more you have changed, the more the entropy is changed by mixing A and B together. Notice that at the edges here, the derivative is very, very large. It's essentially plus or minus infinity at 0 and 1, so that the effect of adding a single molecule of impurity has a gigantic effect on the entropy. That there's a big, big push here at the extremes for the effects of adding just a little bit of impurity to the system. If we then take our unmixed, again, a straight linear combination of the Gibbs free energy of A and the Gibbs free energy of B, and subtract from it some amount of something multiplied by this delta S of mixing, then we're going to get a concave down, or sorry, a concave up structure here that just a little bit of B added to A starts the Gibbs free energy dropping. There will be some minimum down here, but in general, the mixed case will have lower Gibbs free energy than the unmixed case. And so for ideal mixing, where the interaction between the molecules doesn't matter, or where the molecules themselves are the same size and the interaction between the molecules is the same regardless of whether they are like particles or unlike particles, then there will always be, better from the Gibbs free energy standpoint to be mixed than unmixed. And any two substances which satisfy this condition for an ideal mixture will always mix together. A second corollary is that since that that function of the entropy. Since the mixing term is so sharp at the extremes, then even in cases where we're not in an ideal mixing condition, the entropy term at the edges will be so sharp that even for there will always basically be a small amount of impurity in any system. No matter how much we try and unmix it, if there are two substances, the equilibrium phases are always going to have probably just a tiny bit of impurity in them. Well, let's investigate this question of what happens for non-ideal mixtures, right? So when it does matter, for instance, how the molecules interact, when, for instance, the unlike molecules are less attracted to each other than the like molecules. For instance, oil and water is a case where the oil molecules stick to each other better, and the water molecules stick to each other better than oil and water does. Oil and water are less sticky to each other than oil is to oil or water is to water. And so this means that in mixing a pure water substance or a pure oil substance with a bit of the other means that we increase the thermal energy of our system, right? So if our molecules are less attracted to different types than they are to the same types, then we have an effect here again. If our fraction is pure A on the left and pure B over here on the right from 0 to 1, then the change in the energy in going from mixed and unmixed is going to be something like that. Again, it's going to be large in the middle when we have the most of the A particles interacting with B particles. It's going to be smaller over here where we're mostly A or mostly B. But unlike the entropy, the slopes here will be finite, whereas with the entropy curve, the slopes were infinite at the edges. Well, let's look again at where that shows up in terms of the Gibbs free energy. Well, we've changed now both the entropy by mixing and the internal energy by mixing. So we're going to have some minus of that entropy term, which is the amount of minus is going to be determined by the temperature. But we're going to have some plus here of the energy term. All right. And so at low temperatures, when temperature is approaching 0, the entropy term isn't really going to matter much, and the change in the Gibbs free energy for mixing would lead to a increase in the Gibbs free energy. So if we look here at figure 526, you can see here that again there was this linear shift from A to B for the pure substances without mixing, but when we mix them together, that increased the energy internally like so that the Gibbs free energy at 0 temperature, where the entropy isn't showing up at all, if we're at absolute 0, the Gibbs free energy increases as we go into the mixed regime. And so we would get either pure A or pure B, but it's not going to want to be mixed anywhere in between, because the Gibbs free energy of non-mixing would be less than the Gibbs free energy of the mixed case. As we increase the temperature, however, as we increase the temperature, then that minus TS term here becomes a bigger and bigger factor. And so we add to this concave up or concave down term a little bit of concave up, and the higher the temperature, the more that concave up term starts to dominate, so that they're at the highest available temperature down here, you might have a pure concave up system. And somewhere in between absolute zero and the highest available temperature for our system, there will be a mixture of, at the edges where we have essentially infinite slope, you always get a little bit of mixing in the system. But then anywhere in between, it's a question of which is larger, the unmixed Gibbs free energy or the mixed Gibbs free energy. All right, so again, pure A over here, pure B over here. So there's our fraction. And if those are the unmixed fraction points, so that this dotted line here represents an unmixed combination of A and B. So along here, this is the Gibbs free energy for the system in its unmixed state. There will be a little bit of a dip here at either end because that entropy term is very sharp, and if there is a non-zero temperature, then even just a little bit of temperature will generate some small amount of mixing if you have a small amount of impurity. But if you have somewhere in here, the mixing energies are the energy of the change in the energy term is still dominating over the change in the entropy term. And so everywhere for fractional amounts everywhere in here, we will have unmixed at a given finite temperature. Here we'll have mixed. Here we'll have mixed. So just a little bit of A will get dissolved into, or a little bit of B will get dissolved into A, or just a little bit of A will get dissolved into B. But if we're in here with a large amount of both A and B, and a finite temperature such that the interaction energy change overpowers the entropy change, then we will have an unmixed region in here. And so we say that this material has a solubility gap, that for very low or very high amounts of substance B, we can be in a mixed state, but for more even amounts of A and B, we're in an unmixed state. So you can dissolve a tiny droplet of oil into a large amount of water, or you can dissolve a tiny droplet of water into a large amount of oil, but large mixtures of oil and water will always spontaneously separate because the Gibbs free energy is lower for the unmixed combination of oil and water than it was for the mixed combination of oil and water. In the case of oil and water, the critical temperature at which you would need, to pull the mixture all the way down here to being concave up everywhere is actually above the boiling point of water. So for most oil water mixtures, you can't ever get significant amounts of oil dissolved in water or significant amounts of water dissolved in oil, because the water will just boil off into steam before you reach that point. But for instance, if you have here a mixture of water and phenol, the critical temperature for phenol to reach a mixed point here is 67 Celsius, so below the boiling point of water. Below 67 Celsius, you will either get, or if you have small enough fractions of water and phenol, then they can mix together, but in general, you'll be in the unmixed phase. And so we can get, in general, you expect a diagram sort of like this. At the edges, you can always dissolve a little bit of your substance into a large amount of the other substance. You can always absorb a little bit of impurity, but if you're below this temperature here, wherever it is, that would give you concave up at that mixture point, at that X point, then you'll have separated phases, and that for whatever the temperature is between the highest possible temperature that your mixture can sustain and your absolute zero, there will always be a point over here where it's concave up for some maximum amount of fraction. And there's always a point over here at high where it's going to be concave up for some maximum amount of fraction xb. But anywhere in between that, you will have an unmixed a combination of A and B, because the homogeneous mixed version has larger Gibbs free energy than just mixing, or than just a combination of unmixed A and B. And so for any given fraction x, there is a minimum temperature which will bring this energy hump down below the entropy hump, and that's what's represented on this graph. The minimum temperature needed for a x fraction to dissolve in the other. This isn't only true for liquids or gases. You have a similar process that takes place in solids, with the added effect that for solids, it's not just the interaction between individual molecules that start to make a difference, but because solids form crystals and a crystal lattice, if the two different substances, A and B, have different shaped crystals, then again, you can absorb small impurities without destroying your crystal lattice very much. But as soon as you start getting appreciable amounts of impurities that want to form their own crystal structures, then this introduces a lot of distortion and a lot of stress into the crystal matrix, and so the energy terms start to rise very quickly, and you get diagrams like this where you can see the Gibbs free energy for A and, or for, in this case, alpha and beta for different mixtures, and you can see these energy terms rise very quickly. And again, you can absorb small amounts of impurity into either pure A or pure B structures, but it's much, much harder in many cases with these different crystal structures to mix alpha and beta together, and you tend to have essentially crystals of pure alpha and crystals of pure beta forming macroscopic chunks instead of mixing microscopically. And so you'd see, for instance, in granite, in many granites, you see that you can see the individual materials forming large crystals next to one another, and a lot less of the more chemically homogeneous structures forming. All right, so now that we've looked at this question of whether a mixture of materials will be miscible, whether you can make a mixture out of it, or whether or not there will be a solubility gap, leaving mixtures of relatively middle mix ratios as chunks of unmixed stuff like oil and water, or whether or not you have a solution where the for all mix ratios, the solution can remain miscible, so that both components can be mixed down at the microscopic level. That's what we mean by miscible. That your substances will remain mixed down all the way at the microscopic level, as opposed to sort of blobbing up and forming isolated chunks of much larger chunks, macroscopically large chunks of pure or mostly pure materials, instead of mixed right down at the microscopic level. So now that we've got the tools to discuss solubility and whether or not you're going to have a mixture or an unmixed pair of materials, now we can ask the question of what happens when we cross a phase transition, so that the temperature drops from, say, gas phase to liquid phase, or liquid phase to solid phase, in one of these mixed materials. So for instance, we could look at the liquefaction of air, or at least something very much like air. We will be using a mixture of nitrogen and oxygen. So you have we'll look at N2O2 mix with a 79% to 21% ratio. So basically the two major components of air without the little bit of argon and touch of other stuff. Now, if you look at pure O2, pure O2 has a liquefaction, or a condensation point of, or a boiling point at 90 Kelvin, whereas nitrogen has a boiling point at 77 Kelvin. And so above 90 Kelvin, and the Gibbs free energy curves for oxygen and nitrogen are such that they are concave up for all mix ratios from 0 to 1, and so the two substances are completely miscible in the gas phase, which is good. We don't wander around hitting pockets of nitrogen and pockets of oxygen as we walk around in the world. And indeed, below 77 Kelvin, they are completely miscible in the liquid phase as well. That if you mix liquid oxygen and liquid nitrogen together, they will mix completely down to the molecular level, and you won't get any separation like you do with oil and water. But something odd, or perhaps unexpected, happens when you reach the area between 90 Kelvin and 77 Kelvin. So for instance, you might think that, well, as we go below the 90 Kelvin point, the oxygen will start to liquefy and condense out, and we'll start to get a mixture of pure oxygen with some nitrogen. But that's not exactly what happens. You do begin to condense liquid out, but it's not pure oxygen to begin with. It's a higher mix ratio of nitrogen to oxygen, but not pure oxygen. And to understand why, we have to look a little bit at what's going on. All right, so like I said, at all temperatures, the curves for nitrogen and oxygen, the mixture curves that we were looking at, were concave up. So the Gibbs free energy is concave up everywhere for both the liquid and the gas phases. But since the change in the Gibbs free energy with respect to temperature is minus the entropy. As we lower the temperature, the Gibbs free energy is going to increase for both the liquid and the gas phase, but the gas phase has larger entropy, and therefore the gas curves will rise faster than the liquid curves. So, all right, so as I was saying, if we start with a high temperature, so above the boiling point of substance B, and in this case we're assuming here that substance B has the higher boiling point than substance A does over here. So that in this case B would be the oxygen phase and A would be the B would be pure oxygen, A would be pure nitrogen. So if we start above the boiling point for the pure B substance, then you can see here the Gibbs free energy for the liquid phase is completely concave up, and so at all fractions of A and B, we have a purely miscible substance, and we'll have a mixed substance. And also at the gas phase, the liquid and the gas phase are both concave up, and so both are would be purely mixed, but the gas phase everywhere at all mixtures has lower Gibbs free energy than the liquid phase does at all mixtures. And so the at higher than the boiling point of pure B, the entire substance will be a mixture, a homogeneous mixture of A and B at all mix ratios. And as the temperature drops, again, both of these curves will rise, but the gas will rise faster than the liquid because the entropy of the gas phase is larger than the entropy of the liquid phase. And so the curve, the whole gas curve here will rise faster than the liquid curve will. And so eventually you get to a temperature where for pure B, the gas and the liquid phase have the same Gibbs free energy. And this is where the phase transition would occur in a pure substance. As the temperature is lowered between A and B, then for some mix ratios, the liquid phase has a lower Gibbs free energy, and for some mix ratios, the gas phase here has a lower Gibbs free energy. So for very low B abundance, you would expect to still be in the gas phase, and for very high B abundance, you would expect to be in a liquid phase. And the temperature can continue to drop down here until we get to the crossover point at the other end, so that you've reached the boiling point of the pure A substance. And now for all mix ratios, the liquid phase is lower than the gas phase. And as you continue to lower temperatures, that continues to be true. And since the liquid phase is the lower Gibbs free energy, that will be your equilibrium phase. And so below the boiling point of the lower of the two substances, you'll be in pure liquid, and above the boiling point of the higher of the two substances, you'll be in gas phase. And above and below those 2 points, you will have a homogeneous mixture in either the gas phase or the liquid phase. But let's take a closer look at what happens in between. And I'm actually going to redraw sort of this middle diagram here and exaggerate things a little bit more, because I think it's a little bit hard to see on this figure. So let me go back here and just redraw that part of the diagram, and I'm going to use colors here. So I'm going to use a blue color to represent the unmixed gas phase. And again, we have a plot here running from pure A on this end to pure B over on this end. And so we have a gas phase maybe that looks a bit like this in the unmixed gas phase. And I'll use red here to be the unmixed liquid phase. Like that. So both of them are concave up. This is the liquid, and this is the gas, both unmixed and unmixed liquid and unmixed gas. But notice here that we can draw a tangent point here where the tangent to the curve over here and the tangent to the curve over there are the same. And in other words, we can draw a straight line between those 2 points. And this would represent an unmixed combination of both liquid and gas. This is the unmixed liquid over here. This is the unmixed gas over here. And there is a straight combination of those two that would allow us to get below the Gibbs free energy we would have here. So that, in other words, a bit of liquid at a much higher mix ratio and a bit of gas at a much lower mix ratio would have less Gibbs free energy than gas here in the middle. And so instead of mixing in this zone here, what will happen is that you will have this a solubility gap, just like we saw earlier, and you'll get an unmixed combination of A in gas form and B in liquid form, but not at the mix ratio we went into, but at very different mix ratios. And so if we go back to, and I'm just going to zoom in on this figure now over here. If we look at, for instance, this temperature 3. So this temperature 3 is somewhere between B and, or somewhere between the boiling point of B and the boiling point of A, but closer to the boiling point of B. And you can see here that these 2 points are the ones connected by that tangent curve, and between those 2 points, which correspond down here, that we're at the same temperature T3 below the boiling point of B, but we'll have liquid forming at a higher mix ratio and solid or gas staying, but now at a lower mix ratio, to make up for the fact that we've brought more of the B in at the higher mix ratio than we would otherwise. If we were coming in somewhere in here and we were at this temperature T3, instead of being right here in the middle, we'd have liquid forming over here and gas forming over here. As we go to lower temperatures, that region where we split between liquid and gas goes downward, and we get a region here in the middle, and then finally at even lower temperatures a region here. So if we add up all the places where this tangent curve intersects the liquid line at different temperatures, then that gives us this bottom curve. And if we add up all the places that this tangent line intersects the gas curve at different temperatures, then we get this upward curve here. And at a particular temperature between those, if say we have a 50-50 mix, then for instance, then we would, if we had a 50-50 mix of gas coming into it, then what happens is as we hit this barrier, right? And here we're going to actually look at this diagram here shows us the actual curves, experimentally measured curves for the nitrogen-oxygen phase. So these are the gas phase, or the gas points on the top line and the liquid points on the bottom line. And if we come in, for instance, at a 21:79 ratio, like we would have in air, again above the boiling point of oxygen, we have a pure mixture of oxygen and we have a ratio of oxygen and nitrogen that is pure, that is completely mixed. It's completely miscible. As we hit the freeze or the liquefaction point for pure oxygen, our mixture remains in gas form, and it remains in gas form for quite a while. We go way below the 90-degree boiling point of oxygen, all the way down here to just under 82 degrees Kelvin, 82 Kelvin, before we finally hit the point where we're going to have to leave a pure mixture of gas. And then what's going to happen here is, again, the liquid is our red line, so I will go ahead and follow the red. So the liquid, when it hits this point here, then goes out over here, and so immediately below that 82 degree mark, it shows up over here, and then goes, comes down, hang on. All right, excuse the interruption. So we come over here, and now we're at a much higher, almost 50-50 mix of liquid, or of the nitrogen and oxygen. Way more oxygen than we would usually have had. Meanwhile, the gas has come down over here and comes across over there. So the gas phase over here is at a much lower nitrogen or much lower oxygen abundance, almost pure nitrogen, by the time it crosses over. Once we get below this point, which is, notice, above the boiling point of nitrogen, now we finally reach the point here where we can continue to drop now as a pure mixed liquid in a purely homogeneous liquid mixture of nitrogen and oxygen to lower temperatures. Again, above the boiling point of liquid nitrogen, we reach this boiling point, or the liquefaction point for the mixture of oxygen and nitrogen. Oxygen and nitrogen obviously aren't the only ways that this could work. There are some solid, liquid-solid boundaries where you would also get miscible fluids in, or miscible fluid in liquid form. And as long as the crystal structures are compatible, then you can get similar effects in the solid phase as well. Again, it depends on the crystal structures strongly. What we'll look at next here is what happens when you have a miscible liquid mixture that then descends below the freezing point, but in the much more common case where the two substances in our mixture do not have sort of compatible crystal structures, and what happens then. So in the case when we have a miscible liquid, so for instance here, we can see that the liquid phase, is concave up at all mix ratios, and therefore when we are in the liquid phase, the substance will be a homogeneous mixture at all mixture ratios. But that the solid phase is represented here by alpha and beta. Those solid phases will give us a breakdown where the substance as it transitions into solid will not remain a pure homogeneous mixture. For concreteness, in this diagram again we've assumed that that substance B has the higher melting point than substance A does, and again, just like we saw with the liquid and the gas diagram, as the temperatures drop, all of these curves increase upward. All of the Gibbs free energy curves rise, but liquid has more entropy than the solid phases, and so the liquid curves will rise faster than the solid curves. And so if we're above the melting point of pure B at some point, as the temperature drops, eventually the liquid curve here will intersect with the beta curve, representing the crystal structure, the Gibbs free energy of the crystal structure of pure beta. And what you'll see is that there is this region here, again, where that tangent line intersects the liquid on one side and the solid phase on the other. Way over here at the edge, right, we'll get, we will form solid beta. We will form betas way out here. This will just form crystals. But in here, we're going to have a mixture, a non-homogeneous mixture, a mixture of a liquid over here at a lower mix ratio, and then forming a solid over here at a higher mix ratio. So if we came in again at a mix ratio like this, then we got to this temperature, well then suddenly we would be forming crystals at a mix ratio way over here, and still have a liquid phase at a much lower beta ratio down here. As the temperature drops, eventually we would intersect the A curve over on the other side, and that'll set up a different region on the left where we get both alpha and liquid. And again, the alpha will be at a much lower mix ratio and the liquid at a much higher mix ratio. So it's kind of like what we just saw before with the liquid gas ratios, except that now we form kind of two regimes depending on what our mix ratio is, right? So if we're at high-ish mix ratios over here, then as we descend to lower and lower temperatures, first of all, we have to get well below the melting point of B, before we split. But then we will form, as we cool off, we will form crystals way out here at a much higher purity level and have liquid way over here at a much lower purity level. And then as we go to lower and lower temperatures, we will get we will get more and more impurity forming in our solid phase, and the remains would be less and less. And the region of mix ratios that will have this unmixed combination of solid beta plus liquid will get larger. If we come in it from down here with a much lower ratio, the beta won't form first, the alpha will form first. And again, the alpha will form with with relatively pure alpha and a mixture of liquid, but then as we lower and lower the temperatures, the purity of the alpha will degrade. And this region over which we have a non-homogeneous mixture of alpha and liquid will get larger. Now, eventually, these tangent curves, which are getting flatter and flatter as the liquid curve smashes upward into the two solid curves, eventually these two tangent curves will meet somewhere over here at a point we call the eutectic. And this point is interesting. If you have exactly that mix ratio, then first of all, that's the mix ratio that will give you the lowest melting point, right? It'll be a melting point that is lower than both the melting point A and the melting point of B. It's lower than the melting point of both pure substances at this particular mix ratio, and below this temperature here, what we will get is a no liquid at all, but then a non-homogeneous mixture of solid alpha and solid beta. So you'll get large chunks of alpha crystals and large chunks of beta crystals. And the alpha crystals will have purity way over here, and the beta crystals will have purity way over here. There's always a little bit of impurity because, again, as we saw, just the first time you add a molecule of impurity to an otherwise pure system, the entropy increases. So there's always a little bit of impurity. But as you go to lower and lower temperatures, the impurity in the crystals, which are non-homogeneously mixed, will be smaller and smaller, so that you'll get purer and purer crystals as the substance cools, but that you're going to form in general, at least in equilibrium, you'll form this mixture of crystals of alpha and crystals of beta, of relatively pure form, but not entirely pure. Now, eventually, you're going to the time to reach equilibrium in a solid and mix the purity of these crystals out. Eventually, that time can get very, very long, and so in a practical substance, there is some effective freeze-out temperature below which the purity of the crystals doesn't tend to actually occur at finite time, even over geological timescales, if we're talking about the formation of these sorts of substances in various crystal forms. But in general, this is the kind of behavior you could see, and there are a number of substances that show these useful phases. Your book describes here the behavior of lead solder here, which is a mixture of lead and tin, and typically solder would be a mixture of lead and tin right at this eutectic point, so that you can lower the melting point of the solder here quite a bit, and also that you get a relatively decent mixture of the grains that is relatively strong once you cool down below this final eutectic melting point. Similar effects would be, for instance, why one would salt roads in the winter to melt ice around here and things like that. And there's a homework problem that will have you think about that as well. All right, so that's where we're going to wind up our discussion today. Later in the week, I will post a discussion where we talk about the behavior of these mixed systems at the very dilute end, where we're way out on the purity edge out here. And there's a different sort of approach that we can take for those problems. All right, until then.